What is going on, my guys? How's it going? Shout out to Coursera for sponsoring the first ever stream. Never had one of these before. They wanted to do a code with me stream, and I was like, can we do machine learning instead? Because that stuff's hard. I think a lot of people are interested in it, so I thought we'd do it together. So shout out to Coursera. Why can't I say that? Why is that so difficult? I'll just chill out for a sec till some people get here. What's going on, guys? All the way from UK. Red, hey dude, what's up? How's it going? Salute. It's okay, I'm here. We were lost without you. Brian. The Nomon. What's up, man? Let me post this to Discord real quick, then we'll be alright. Did you guys get the notification? By the way, the link for Coursera is in the description. Python. No Python yet. Looks good to me. Let's get started. Hey, from Norway. Got the notification. Sweet. From Florida. 42CT. What's up, dude? I was just reading your message on LinkedIn, I think. Yeah, so there's not actually a whole lot of programming involved yet until we get to like week 2 or 3. But I just want to run over the model representation and the model, like the cost function and how all this works. So prepare your math. Canada? Dude, what's up? Music might be too loud. I might have to turn this down. All right. I guess we'll start, or let's do supervised learning and then unsupervised learning, just to catch everybody up first. Then you guys can correct me. Is the course free? You can audit it for free, or if you want to get like the official, like certificate from Stanford and Coursera, then you pay for it. But you can't get like graded. Bosnia, what's up? What language are you going to be using? I don't know, John. I don't know. Haven't got that far.
In this video, I'm going to define what is probably the most common type of machine
We know if it's too quiet.
which is supervised learning. I'll define supervised learning more formally later, but it's probably best to explain or start with an example of what it is, and we'll do the formal definition later. Let's say you want to predict housing prices. A while back, a student collected datasets from the city of Portland, Oregon, and let's say you plot the dataset and it looks like this. Here on the horizontal axis, the size of different houses in square feet, and on the vertical axis, the prices of different houses in thousands of dollars.
Okay, so I can kind of just explain this so we don't have to go through the 12-minute video here because we only got about an hour and I have to go. So basically, you give an input and you're trying to predict an output and you're trying to use machine learning to get that output. So, you know, that's essentially what we're going to run through for about 12 minutes.
So, given this data,
Brandon, what's up, dude?
let's say you have a friend who owns a house that is, say, 750 square feet.
Let me skip through this, see if I can like find some correct points. Regression, so that's like predicting an output, and then unsupervised, or that's, yeah. Then we have classifications, which is like, based on this output, it's this, and then based on this output, it's this. And he talks about like some health issues. So this would be classifications. Syntax. Final interview with the CTO for what looks like your dream job. Why are you nervous? You gotta have that abundance mentality. If you go in there acting all nervous, you're gonna pick up on that, and you're not gonna have very much power. Try to hold on to that power, man. So I'll just play it, and then I'll talk about it because I already did these.
Benign. So let's say your data set looks like this, where we saw a tumor of this size that turned out to be benign, one of this size, one of this size, and so on. And sadly, we also saw a few malignant tumors. So one of that size, one of that size, one of that size, and so on. So in this example, I have 5 examples of benign tumors shown down here, and 5 examples of malignant tumors shown with a vertical axis value of 1. And let's say you have a friend who tragically has a breast tumor, and let's say her breast tumor size is maybe somewhere around this value. The machine learning question is, can you estimate what is the probability, what is the chance that the tumor is malignant versus benign? To introduce a bit more terminology, this is an example of a classification problem. The term classification refers to the fact that here we're trying to predict a discrete value output, 0 or 1, malignant or benign. And it turns out that in classification problems, sometimes you can have more than two values for the two possible values.
I think he could move his mouth away from the mic a little bit.
Maybe there are 3 types of breast cancers, and so you may try to predict a discrete value output 0, 1, 2, or 3, where 0 may mean benign tumor, so no cancer, and 1 may mean type 1 cancer.
So he doesn't actually write the algorithm to do this here. He's just showing you, are we predicting if it's 0 or 1, and this is classification-based machine learning. And the other one over here was regression. Yeah.
Okay, 3 types of cancer, whatever type.
Ivan, what's up, dude?
And 2 may mean the second type of cancer, and 3 may mean the third type of cancer. But this would also be a classification problem because there's sort of a discrete value set of outputs corresponding to no cancer, or cancer type 1, or cancer type 2, or cancer type 3. In classification problems, there is another way to plot this data. Let me show you what I mean. I'm going to use a slightly different set of symbols to plot this data. So if tumor size is going to be the attribute that I'm going to use to predict malignancy or benignness, I can also draw my data like this. I'm going to use different symbols to denote my benign and malignant, or my negative and positive examples. So instead of drawing crosses, I'm now going to draw O's for the benign tumors, like so. And I'm going to keep using X's to denote my malignant tumors. Okay, I hope this figure makes sense. All I did was I took my data set on top, and I just mapped it down to this real line.
They just changed it
and started
to symbols,
circles and crosses, to denote malignant versus benign examples. Now, in this example, we use only one feature or one attribute, namely the tumor size, in order to predict whether tumor is malignant or benign. In other machine learning problems, we may have more than one feature or more than one attribute. Here's an example. Let's say that instead of just knowing the tumor size, we know both the age of the patient and the tumor size. In that case, maybe your data set will look like this, where I may have a set of patients with those ages and that tumor size that look like this, and a different set of patients that look a little different, whose tumors turn out to be malignant, as denoted by the crosses.
So basically, classification type learning here is when you get like a key which has a value assigned to it, so you like predict that key. So if you end up getting this circle, right, then it's benign, I think. Whereas the regression one is like we're giving an input value and we're getting out an output value of like price or size or something, rather than just a key value like this. So does this kind of make sense to everybody? You guys want to watch the rest of this? It's kind of long. I'll just keep playing it.
So let's say you have a friend who tragically has a tumor, and maybe their tumor size and age falls around there. So given a data set like this, what the learning algorithm may do is fit a straight line to the data to try to separate out the malignant tumors from the benign ones. And so the learning algorithm may decide to fit a straight line like that to separate out the two classes of tumors. And with this, hopefully we can decide that your friend's tumor is more likely, so if it's over there, that hopefully the learning algorithm will say that your friend's tumor falls on this benign side and is therefore more likely to be benign to malignant. In this example, we had two features, namely the age of the patient and the size of the tumor. In other machine learning problems, we will often have more features. And my friends that work on this problem, they actually use other features like this, which is clump thickness of the breast tumor, uniformity of cell size of the tumor, uniformity of cell shape of the tumor, and so on, and other features as well. And it turns out one of the interesting...
Tara's like, machine learning is basically finding the optimal decision boundary between clusters where the decision boundary can be n-dimensional. Bruh, you gotta use layman terms, fam. You can't just come in here, well, basically, and then you explain it like it's the most scientific thing ever. Calm down with that, Tara. Bring it down.
Most interesting learning algorithms that we'll see in this class is a learning algorithm that can deal with not just 2 or 3 or 5 features, but an infinite number of features. On this slide, I've listed a total of 5 different features, right? 2 on the axis and 3 more up here. But it turns out that for some learning problems, what you really want is not to use like 3 or 5 features, but instead you want to use an infinite number of features, an infinite number of attributes, so that your learning algorithm has lots of attributes of features and cues with which to make those predictions. So how do you deal with an infinite number of features? And so how do you even store an infinite number of things in a computer when your computer's going to run out of memory? And it turns out that when we talk about an algorithm called the support vector machine, there'll be a neat mathematical trick that will allow a computer to deal with an infinite number of features. Imagine that I didn't just write down, 2 features here and 3
He just
features
gets
on
real
right.
close to the
Imagine
mic
that I wrote down
sometimes.
an infinitely long list. I just kept writing more and more and more features, like an infinitely long list of features. Turns out we'll be able to come up with an algorithm that can deal with that. So just to recap, in this class we'll talk about supervised learning, and the idea is that in supervised learning, in every example in our data set, we are told what is the quote correct answer that we would have quite liked the algorithm to have predicted on that example, such as the price of the house or...
Yeah, you guys are like super smart. Oh, Sandermat87, you're the dude that's like, actually, you're completely wrong about everything you said in your video, and then you're like, here's the actual solution, Josh. And I was like, okay. I need caveman terms. Like, I don't have a PhD in math.
whether a tumor is malignant or benign. We also talked about the regression problem.
You guys are way smart.
That means that our goal is to predict a continuous valued output. And we talked about the classification problem, where the goal is to predict a discrete valued output. Just a quick wrap-up question. Suppose you're running a company and you want to develop learning algorithms to address each of 2 problems. In the first problem, you have a large inventory of identical items. So imagine that you have thousands of copies of some identical items.
Oh, we'll let them fight between
You want to predict
themselves.
how many of these items you sell over the next 3 months. In the second problem, problem 2, you have lots of users and you want to write software to examine each individual of your customers' accounts, so each one of your customers' accounts, and for each account, decide whether or not the account has been hacked or compromised. So for each of these problems, should they be treated as a classification problem or as a regression problem? When the video pauses, please use your mouse to select whichever of these 4 options on the left you think is the correct answer.
Alright, so we got one of each, it looks like. So we want to be hacked or compromised. This is a classification problem. Problem 2 is classification. Problem 1 is regression. Large inventory, you want to predict how many of these will sell, so that's an output number over 3 months, right? So we treat problem 1 as regression, it's output problem. Problem 2 is classification because hacked or compromised is classified. Jim, what's up, dude? Jay-Sean, aren't you at work? I don't know, yeah, machine learning is a lot different. Like it's way far away from web dev. You'll see when we get to this cost function here. And then we'll go to the unsupervised learning video here for a sec so you guys can get that. But like, it's just so different. I don't know. Dude's just come, like, I don't know if you guys already know all this stuff. What's the benefit of watching? Submit. Correct.
So hopefully you got that this is the answer. For problem 1, I would treat this as a regression problem because if I have thousands of items,
I think we just got viewers that like to come in and flex their machine learning knowledge.
And treat therefore the number of items I sell as a continuous value. And for the second problem, I would treat that as a classification problem because I might say set the value I want to predict to be 0 to denote the account has not been hacked, and set the value 1 to denote an account that
I'm not struggling.
hacked into.
I'm
So
enjoying
it's
the
like
process.
answers, right? 0 will be
Craig.
1 is malignant. So I might set this to be 0 or 1 depending on whether it's been hacked. And
See, he's talking about classification 0, 1, not hacked. Hacked. Does this guy make sense? I know what you guys want. I know the people that are here that are kind of confused. I know how to explain it to you because I had to rewatch this like 10 times to explain this to my caveman self. This is the first time I've ever done this. I was like, I think everyone's like, machine learning sounds so cool. And then you get into these videos and people are like, well, this is boring. Yeah, well, sorry, you can't have a, robot that just does stuff without doing this. So I thought it'd be a little bit more interactive. Actually, we don't get to the code part till like week 2 or 3 when we have to download Octave. And then we start writing algorithms. And we convert those algorithms to Python or C++. I don't know which one we do in this course, but... yeah, apply everywhere. Get those interviews. Right. All right. So we'll go to unsupervised. The main example he uses here in unsupervised is he writes a algorithm let's say like I'm right here at the microphone. You guys can't see it. Let me point it down. So I'm like right here at the microphone, and some guy is over here at the microphone, and then they swap, and he writes a machine learning algorithm to separate the two voices. So if I'm talking and some guy back here is talking at the same time, can you write an algorithm to like separate these two voices, which is just unsupervised? There's no classification. It's not like, is it this guy or this guy? Because that's not on the input. That's not on the inside. Hopefully that kind of makes sense. Well, you watch it. It's kind of long, but
We'll talk about the second major type of machine learning problem called unsupervised learning. In the last video, we talked about supervised learning. Back then, we got data sets that looked like this, where each example was labeled either as a positive or a negative example, whether it was a benign or a malignant tumor. So for each example in supervised learning, we were told explicitly what is the so-called right answer, whether it's benign or malignant. In unsupervised learning, we're given data that looks different.
all right. Well, tell Andrew that in his example.
That doesn't have any labels, or that sort of all has the same label, or really no labels.
Yeah. See, no labels. That's what I said.
Data set, and we're not told what to do with it, and we're not told what each data point is. Instead, we're just told, here is a data set. Can you find some structure in the data? Given this data set, an unsupervised learning algorithm might decide that the data lives in two different clusters. So there's one cluster, and there's a different cluster.
See, they're not labeled. So this is one guy over here talking, these circles, and then this other circle group is another guy over here talking, or multiple people talking, or a data set talking. And the unsupervised learning algorithm, right, doesn't know that these are two different things. It just knows that they're two different sets of data, and then it separates them.
Cluster, and the unsupervised learning algorithm may break this data into these two separate clusters.
The reason I have to show you this is for the cost function.
And this turns out to be used in many places. One example where clustering is used is in Google News. And if you've not seen this before, you can actually go to this URL, news.google.com, to take a look. What Google News does is every day it goes and looks at tens of thousands or hundreds of thousands of news stories on the web, and it groups them into cohesive news stories. For example, let's look here. The URLs here link to different news stories about the BP oil well story. So let's say I click on one of these URLs, what I'll get to
Am I
is
drinking?
a page like this. Here's
The healthiest drink ever.
About the BP oil well spill story. So BP kills Macondo, which is the name of the spill. And if you click on a different URL from that group, then you might get a different story.
That's a good question, Jim.
Story about again the BP oil spill. And if you click on yet a third link, then you might get a different story. Here's the UK Guardian story about the BP oil spill. So what Google News has done is looked at tens of thousands of news stories and automatically clustered them together, so the news stories that are all about the same topic get to display together. It turns out that clustering algorithms.
I think if he just spent $20 on a mic instead of $6, this course would be leaps and bounds better.
Here's an example of DNA microarray.
Later, Craig.
The idea is you have a group of different individuals, and for each of them, you measure how much they do or do not have a certain gene. Technically, you measure how much certain genes are expressed. So these colors, red, green, gray, and so on, they show the degree to which different individuals do or do not have a specific gene.
Just
And what
put
you do
7 in there,
with
Nathan.
clustering
Holy crap.
algorithms-
What just happened?
So this is unsupervised learning because we're not telling the algorithm in
My
advance
ears.
that these are type 1 people, those are type 2 persons, those are type 3 persons, and so on. And instead, what we're saying is, here's a bunch of data. I don't know what's in this data. I don't know who's in what type. I don't even know what the different types of people are. But can you automatically find structure in the data for me? Can you automatically cluster the individuals into these types?
I'm trying to turn him up. Like, he's full blast volume.
Giving the algorithm the right answer for the examples in my data set. This is unsupervised learning. Unsupervised learning or clustering is used
All
for
right.
much of other
Well,
applications.
that one's going off.
It's used to organize large computer clusters. I had some
Tanvir, what's up, dude?
large data centers, that is large computer clusters. And
All right, so this part's kind of like a little dull, right? You guys are here to watch some entertaining stuff, so let me explain it. So that's what I was talking about. You got speaker 1, speaker 2, different distances away from different microphones right here, and then the algorithm separates the two. So you can decipher, like, one dude's counting to 10 in English, one dude's counting to 10. All right. What is going on? Maybe it's my OBS. I think OBS is losing its mind. He's not doing a live demonstration. I'll show you.
Of two speakers recorded by a researcher. Let me play for you what the first microphone sounds like.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Alright, maybe not the most interesting cocktail party is two people counting from 1 to 10 in two languages, but there you go. What you just heard was the first microphone recording. Here's the second recording.
1, 2, 3, 4, 5.
So now they've kind of like swapped positions, right? So this is the microphone. I don't. What is that
These
noise?
two microphone recordings and give them
Seriously.
to an unsupervised learning algorithm called the cocktail party algorithm, and tell the algorithm find structure in this data for me. And what the algorithm will do is listen to these audio recordings and say, it sounds like the two audio recordings that are being added together or that are being summed together to produce these recordings that we had. Moreover, what the cocktail party algorithm will do is
Jim, what's
separate
up,
out
dude?
these two
I'm
audio
up, Tim. What's
sources
up?
that were being added or being summed together to form our recordings. And in fact, here's the first output of the cocktail party algorithm.
1, 2, 3, 4, 5, 6, 7.
So basically muted that dude talking in Spanish in the
So
back.
it separated out the English voice in one of the recordings. And here's the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9 y 10.
Not too bad. To give you one more example, here's another recording of another similar situation. Here's the first microphone.
1, 2, 3, 4, 5.
All right, yeah. So you guys kind of get it, right? So now there's like music playing in the background, and it separates one guy talking, and then it separates the music, right? So it like mutes the dude talking and amplifies the music, and then it mutes the music, amplifies the dude talking. That's unsupervised learning, right? Just two different data sets. They're separating it. Sounds like you're winning the jackpot or something. But I have all the stuff muted for OBS, so I don't know what's going on. Literally, all I have is display and my video. Everything else is muted, so I don't know what's going on. There's a tip jar. All right, everything's going away. Sorry if you tip and I miss it. Do we really need to learn machine learning AI? Web and mobile dev jobs are safe. Hashtag winning. Apparently I'm winning something. Someone's subscribing somewhere or doing something. I don't know what's going on. Sorry, it's kind of loud. It's like, I'm pretty sure I'm gonna be deaf after this. Yeah, the weird noise is for new subs, but I muted that. It's not available anymore, so I don't know how it's playing. Alright, so you've seen supervised and unsupervised learning. Let's come down here and do this cost and model function.
Our first learning algorithm will be linear regression. In this video, you see what the model looks like, and more importantly, you also see what the overall process of supervised learning looks like. Let's use our motivating example of predicting housing prices. We're going to use a data set.
All right, pull out your pen and paper, boys. It's about to get into math.
Oregon, and here I'm going to plot my
XSplit costs money.
a number of houses
And it's
that
not
were
as good.
different sizes that were sold for a range of different prices. Let's say that given this data set, you have a friend that's trying to sell a house, and let's say your friend's house is of size 1,250 square feet, and you want to tell them how much they want to sell the house for.
All right, so this is that very, very, very first supervised learning problem, that regression problem. We give the square footage of the house, and then we want to know what the price is going to be, how to estimate that. So this is the model that we're going to be doing here. How much math? You need to know. There's a lot of thetas just here in this very first formula. It's not too bad though. Linear algebra, discrete math maybe. Can you watch all Coursera courses for free? I think you can audit most of them for free. OBS is not bad. I think sometimes it just bugs out. Maybe I have to update it.
Fit a model, maybe fit a straight line to this data, something like that. And based on that, maybe you could tell your friend that looks like you can maybe sell the house for around $220,000. So this is an example of a supervised learning algorithm, and it's supervised learning because we're given the quote right answer for each of our examples. Namely, we're told what was the actual house, what was the actual price that each of the houses in our data set was sold for. And moreover, this is an example of a regression problem where the term regression refers to the fact that we're predicting a low value output, namely the price. And just to remind you, the other most common type of supervised learning problem is called a classification problem, where we predict discrete valued outputs.
So you get zeros or ones for classification.
We are looking at cancer tumors and trying to decide if a tumor is malignant or benign. So there's a 0-1 value discrete output.
Right, so imagine just like what you can talk about now. Now that you know about supervised learning, regression, classification, and unsupervised learning, at least you can talk about it and not be totally just like machine learning is good. Are you moving to machine learning? I'm not moving to machine learning. I'm just doing it because I want to learn about it. It's good knowledge to have. To be honest, I don't know what I'm doing. I just do things.
In this video, we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data.
Here we go.
In linear regression, we have a training set like that shown here. Remember our notation. M was the number of training examples, so maybe M equals 47. And the form of our
let me show you the model representation right here. So we got the training set. X is the square footage, living area of the house, but I don't know why he just doesn't call it square footage, but you have the square footage, you have the learning algorithm H here, right? So training set, this is all the data you're going to use, your little, like the example data that you're using to compare with. Then you have your learning algorithm, which is the actual learning algorithm with the code part, this piece here. Then you have H in the middle section, which is what this gets called as a variable pretty much. So H equals this stuff up here. And then you have your output, which is the price of the house in this specific model. Does this make sense to you guys? That's kind of how I feel, Ivan. I mean, I just do things. Like I want to learn about something, I'll go learn about something. I mean, I have a plan, but I just do things. All right. Do I conduct a live Q&A for web dev separately? We do daily streams. So, all right, we'll hit up this cost function. Now you guys have seen that.
In this video, we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data. In linear regression, we have a training set like that shown here. Remember our notation. M was the number of training examples.
Right, so this M47 right here, that was the training set. I wish I could... Hold on. This is good to have. All right.
In this video, we'll have a training set like that shown here. Remember our notation. M was the number of training examples, so maybe M equals 47.
See, the
and
training
the form
set
of our hypothesis,
here,
which we use to make predictions, is this linear function.
This training set.
To introduce a little bit more terminology, these theta 0 and theta 1, right? These theta i's are what are called the parameters of the model. And what we're going to do in this video is talk about how to go about choosing these two parameter values, theta 0 and theta 1. With different choices of the parameters theta 0 and theta 1, we get different hypothesis functions. I know some of you will probably be already familiar with what I'm going to do on this slide, but just to review, here are a few examples. If theta 0 is 1.5 and theta 1 is 0, then the hypothesis function will look like this. Right? Because your hypothesis function will be h of x equals 1.5 plus...
All right, so are you ready for some math here? You ready for some math here, boys? This is what we do. This sets your y value, and the x, or this theta 0 sets your y value, basically, your starting point. And then this theta 1 is your slope. So it has a slope of 0, right? No slope on the line, so it's a flat line. So for example, here on the second one, you got this theta 0, 0, which means it's going to start right there in that little corner, and it's going to have a 0.5 slope, right? And then you can figure out what this one is, right? So it starts at 1, and then it goes up 0.5, so it would be like that. That make sense? I'm out. See you on the next one. There's no calculus here. It's just variables. I don't know why he chooses these variables, but hopefully that makes sense. Just basic graphs. You guys remember how to do the slope and calculate where it starts? Remember that 1/2 over 1/2 times, I forget the formula, but you guys remember how to calculate the slope of the line. M1 minus M2 some. That's what's going on here.
0 times x, which is this constant value function that's just flat at 1.5. If theta 0 equals 0, theta 1 equals 0.5, then the hypothesis will look like this.
Yeah, Mumtaz knows.
To this point 2, 1. since you now have h of x, or really h substrate theta of x, but sometimes I'll just omit theta for brevity. So h of x will be equal to just 0.5 times x, which looks like that. And finally, if theta is equals 1 and theta 1 equals 0.5, then we end up with a hypothesis that looks like this. Let's see, I should pass through the 2 point like so, and this is my new h of x, or my new h subscript theta of x.
That makes sense. That makes sense to you guys. Starting point, theta 0, slope, theta 1, multiplied by x, which we don't get a value for, so it just stays a variable. Grow a beard and get a MacBook Pro. Not buying a MacBook Pro. I don't waste money on garbage. I'm just kidding. I'm not spending the money on to get a MacBook Pro. And I'm not growing a beard because I just look homeless.
Remember, I said that this is h subscript theta of x, but as a shorthand, sometimes I'll just write this as h of x.
Alright, so I'll let you guys do this. So what is the solution for this? A lot of thetas. There's just 2 thetas, 0 and 1. We could call them x and y if we wanted to. That'd probably make more sense, but we're not. We're calling them thetas. This is what I always did when I was in school. I would take this math, and then I would convert it to variables that made sense to me. You know what I mean? Like, why we got all these symbols, and when it's really, like, we got a XY graph, why don't we just use these? You're not on this level yet? It's just math. It's just basic XY math. I'm trying to explain it super easy. Right, so theta 0 is your starting point. Where are we starting? So it would be 0.5, right? Between 1 and 0, 0.5. And then we have our actual slope, which is probably like 1. I would say this is like 1 or 0.5. I don't know. It's kind of hard to tell when it starts right here. I'm going to say that's 1. So we can tell right here 1, 1.5, about 1. .5x and then 0.5. Yeah, 0.5 and 1. Daniel's got it. Let's see. Oh, there's the solution, right? So theta 0, the x starting position, theta 1 is 1. Hit that submit, correct. Boom, done. Look, we're machine learning engineers already, guys. Easy.
In linear regression, we have a training set, like maybe the one I plotted here. What we want to do is come up with values for the parameters theta 0 and theta 1, so that the straight line we get all of this corresponds to a straight line that somehow fits the data well, like maybe that line out there. So how do we come up with values theta 0, theta 1 that corresponds to a good fit to the data? The idea is we're going to
basically is you want to find a good starting point and a good slope to fit your data points, right? So you got all these x's here, and you want to find out what is a good formula, right? What's a good starting point? Where we're going to start here on this x, and what's a good slope that would kind of go through the middle of it? So that's what he's saying.
Choose our parameters theta 0, theta 1, so that h of x, meaning the value we predict on input x, that this is at least close to the values y for the examples in our training set, for our training examples.
Okay, so the reason why he used theta 0 and theta 1 instead of x and y is because these values, he's calling these little x's x and y values. Just in case you guys were confused. I like how the stream went from 68 viewers to 44 because they're like, nope, math, I'm out. Is this free? You can audit it for free.
So in our training set, we're given a number of examples.
I'm not sure if you can on this one actually.
And we know the actual price it was sold for. So let's try to choose values for the parameters so that at least in the training set, given the x's in the training set, we make reasonably accurate predictions for the y values. Let's formalize this. So in linear regression, what we're going to do is I'm going to want to solve a minimization problem. So I'm going to write minimize over theta 0, theta 1. And I want this to be small, right? I want the difference between h of x and y to be small. And one thing I'm going to do is try to minimize.
Right, so we can kind of skip this part. He's basically just deriving the formula for us. You remember when you were in math class and the teacher would like derive the formula for you? And then you'd be like, well, why didn't you just give me the end formula so that we can do this? That's what's happening right now. You remember that? That's what he's doing. So I'll skip through this so you can see. Oh, yep, there we go. And then I'll convert these back to thetas. There's your training samples, which are these numbers here. 1/2, blah, 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 which cancels out. Blah, blah. We got some more formulas, deriving some more formulas, and then it gets this longer formula, which eventually turns into a simple formula. We all been there. Y'all dudes who went to college. Yeah, so in the next video, we'll take a look here at the actual cost function. This is what he wrote out. And this is like the official version up here. Ooh, that highlight though. This is the official version, which gets simplified, but you'll see in the next video. It's not as bad as you think. Is this regression? This is linear regression. Which means we give an input to a training set and we get an output like a price. I've already done some of this video, so I'll keep it going. There's some reason behind derivation. Yeah, there is some reason behind derivation, but there are so many algorithms out there right now that are already really popular that you can just use those algorithms. The main problem isn't the algorithm, it's the data that you're feeding it. Are you feeding the algorithm the right data? Because there's so many algorithms out there that are already pre-made. You don't need to reinvent the wheel, right? So the cost function that he just made, he mentions in the video that this is a very popular algorithm for cost. So like they're all pre-made pretty much. Unless you want a job just making algorithms. I don't know what you would do for that. Most of the time you find the algorithm, figure out what data you need to give it, then look to see if that's giving you the right output. But I was never one to be like, wait, hold on, why are we deriving that? And how did you come to this conclusion? Like, I was never that guy. I was just like, can you just give me the formula so I can apply it, please? Thank you. Like, there are two types of people. There are people that invent new things, that derive new formulas, derive new algorithms, and there are people that are like, oh, give me that. You know what we could do with that? And they apply it, right? They figure out awesome use cases for it. It's like when researchers at college invent this new material that's like lighter than air, stronger than metal. They're like, wow, I invented this. And then everyone else is looking at that like, you know what we could do with that? Whereas the dude who invented it had no idea, like he wasn't even thinking about that. So there's two types of mindsets there. I've always been in the mindset of like, can we just apply this and get stuff done? But that's just me. So I'll keep playing.
In the previous video, we gave a mathematical definition of the cost function. In this video, let's look at some examples to get better intuition about what the cost function is doing and why we want to use it. To recap, here's what we had last time. We want to fit a straight line to our data, so we had this form as a hypothesis with these parameters theta 0 and theta 1, and with different choices of the parameters, we end up with different straight line fits to the data, which affects like so. And there's a cost function, and that was our optimization objective. For this video, in order to better visualize the cost function j, I'm going to work with a simplified hypothesis function, like that shown on the right. So I'm going to use my simplified hypothesis, which is just theta 1 times x. You can, if you want, think of this as setting the parameter theta 0 equal to 0. So I have only one parameter theta 1.
Alright, so he does a little gotcha here if you're not paying attention. If you're not paying attention, he tries to make this problem easy for us by setting this starting point theta 0 to 0. So we only have to deal with this one parameter right here. Hi, Adam. That's how you feel in your DiffEQ class? Yeah, pretty much. I mean, to be honest, some guy's job is going to be create these algorithms, and there's another guy's job that's like figure out how to use these algorithms to get what we want. Like, that's just it. That's just, you know, you want both, maybe you're a unicorn. Then good for you, man, but I tend to be on the more applied side. Yeah, so basically setting this to 0, so we don't even have to think about that anymore, which simplifies like this whole equation. But all right, here we go.
And my cost function is...
Because we're starting at the corner of the graph, right? So this would be 0, 0, so we're setting it to 0.
As before, except that now h of x, that is now equal to just theta 1 times x. And I have only one parameter, theta 1, and so my optimization objective is to minimize j of theta 1.
Let me see what's going on here for a sec. h of x I. I forget what this I is. Oh, this is the data point. This is the data point that we're using. And then this is for x, and this is the other data point we're using here for y. So those little x's that were on the graph before, we're plugging them in that little I. So let me show you.
In pictures, what this means is that if theta 0 equals 0, that corresponds to choosing only hypothesis functions that pass through the origin, that pass through the point 0, 0 over there. Using the simplified definition of the hypothesis and cost function,
You can't use an algorithm if you don't understand it. That's not true.
let's try to understand the cost function concept better.
You can understand the algorithm, but you don't have to
It turns
understand
out
how
there are two key
to create
functions
new
we want to
ones.
understand. The first is the hypothesis function, and the second is the cost function. So notice that the hypothesis, right, h of x, for a fixed value of theta 1, this is a function of x. So the hypothesis is a function of what is the size of the house x. In contrast, the cost function, j, that's a function of the parameter theta 1, which controls the slope of your straight line. Let's plot these functions and try to understand them both better. Let's start with the hypothesis. On the left, let's say here's my training set with 3 points at 1, 1, 2, 2, and 3, 3. Let's pick a value of theta 1. So I'm going to set theta 1 equals 1, and if that's my choice for theta 1, then my hypothesis is going to look like this straight line over here. Okay? And I want to point out, when I'm plotting my hypothesis function, my x-axis, my horizontal axis is labeled x, is labeled size of the house over here. Now, I've temporarily set theta 1 equals 1. What I want to do is
The slope
figure
of the
out,
line.
what is j of theta 1 when theta 1 equals 1. So let's go ahead and compute what the cost function is for.
So he's saying, what is j of theta 1? If I back up here. Let me go back. This is the formula. This is the formula right here. So j, theta 0, theta 1, right? Theta 0, he set that to 0, so we can cross that one out. Then we got j is theta 1, which is, he set that to 1. Let's go back, 255 I think it was. Which is this little, like there's a little red X here. I don't know if you guys can see it, but only a real hacker. That's not true. That's a no true Scotsman fallacy that you're saying there, omnipotent voice. Only a real. As soon as you introduce that sentence, only a real. Okay. No true Scotsman fallacy. Google it.
The value 1. Well, as usual, my cost function is defined as follows, right? Sum over my training set of this usual squared error term. And this is therefore equal to this of theta 1 xi minus yi. And if you simplify, this turns out to be that 0 squared plus 0 squared plus 0 squared, which is of course just equal to 0. Now, inside the cost function, it turns out each of these terms here is equal to 0 because for the specific training set I have, for my 3
Understanding the algorithm and deriving it are different.
training examples are 1, 1, 2, 2, 3, 3. If theta 1 is equal to 1, then h of x, h of xi.
Well, maybe the word understanding is the subjective thing we're all getting hung up on.
That is better.
It doesn't matter, right?
Right?
We're just
And
learning.
So h of x minus y, each of these terms is equal to 0, which is why I find that j of 1 is equal to 0.
I brought my girlfriend in here. I was like, look at this. She's like, what are you doing? You already graduated college. I was like, help me understand this. You're in calculus right now. What do these mean again? So let me look at this. So he has theta 1 is equal to 1. How did he get that? How did he get that y? Let me back up.
Value 1. Well, as usual, my cost function is defined as follows, right? Sum over my training set of this usual squared error term.
Just this
And,
usual. Just
this
the
is
usual,
therefore
guys.
equal to
Nothing complicated going on here.
this of theta 1 xi minus yi. And if you simplify, this turns out to be that 0 squared plus 0 squared plus 0 squared, which is of course just equal to 0. Now, inside the cost function, it turns out each of these terms here is equal to 0 because for the specific training set I have, where my 3 training examples are at 1, 1, 2, 2, 3, 3, if theta 1 is equal to 1, then h of x I is equal to yi exactly, and that is better, right? And so
we have 1, 1. So this is 1 minus 1, right? So xy, x here, y here, x minus 1, 1i. Oh. X is 1, y is 1, right? So 2 is, x is 2, y is 2. X is 3, y is 3. So you get 0 squared plus 0 squared plus 0 squared. Why was that so difficult for me to explain? But you guys get what's going on to this fancy math right here? So it's x minus y. You can just, that's what you get. X minus y. 1 minus 1 is 0. And then you get 2 minus 2 is 0. 3 minus 3 is 0, which is what he did. He did this 3 times, right? So that's what this whole long function is over here. He did this 3 times. It was 1 minus 1, which came to 0. 2 minus 2, which came to 0. And 3 minus 3, which came to 0. Oof. All right, moving
h
on.
of x minus y, each of these terms is equal to 0, which is
I wish you would have wrote that out.
j of 1.
Does that make sense to you guys?
0.
I'm trying to explain this math.
So we now know that j of 1 is equal to 0. Let's plot that. What I'm going to do on the right is plot my cost function j. And notice, because my cost function is a function of my parameter theta 1, when I plot my cost function, the horizontal axis is now labeled with theta 1. So I have j of 1 is equal to 0, so let's go ahead and plot that and end up with an x over there. Now let's look at some other examples. Theta 1 can take...
Oh, okay. So I see what's going on. We got j of 1, which is the function of the parameter, which was 0. So j of 0, we're starting on 0, and theta 1, but that's the slope. It why is it? So we're going to have like an upward slope right here, probably?
on a range of different values, right? So theta 1 can take on negative values, 0, positive values. So what if theta 1 is equal to 0.5? What happens then? Let's go ahead and plot that. I'm now going to set theta 1 equals 0.5, and in that case, my hypothesis now looks like this. There's a line with slope equals to 0.5, and let's compute j of 0.5.
So this would be 1 minus 1, 2 minus 2, 3 minus 3 again? Or would it be... Oh, never mind.
So that is going to be 1 over 2m of my usual cost function. It turns out that the cost function is going to be the sum of squared values of the height of this line plus the sum of squared of the height of that line plus the sum of squared of the height of that line, right? Because this vertical distance, that's the difference between, y, I, and the predicted value h of xi, right? So the first example is going to be 0.5.
Oh, I got it.
Squared, because my hypothesis predicted 0.5, whereas the actual value was 1. For my second example, I get 1 minus 2 squared, because my hypothesis predicted 1, but the actual housing price was 2. And then finally, plus 1.5 minus 3 squared. And so that's equal to 1 over 2 times 3, because
3 points.
My training set size, right, I have 3 training examples. And then that's times, simplifying the thing in parentheses, is 3.5. So that's 3.5 over 6, which is about 0.68. So now we know that j of 0.5 is about 0.68. Let's go and plot that. Oh, excuse me, math error. This is actually 0.58. So I'm going to plot that, which is maybe about over there. Okay.
Wait, what? Interesting. So are we doing a problem now? All right, let's do a problem. All right, hypothesis. What are we using for theta 1 here? With m equals 3. Oh, you're going to make us work backwards. So are we just assuming that we're using 1, 1? I don't know. I'm gonna put 0. This shouldn't be selected. Okay. Well, I don't feel like doing the math. Great.
Now, let's do one more. How about if theta 1 is equal to 0? What is j of 0?
Oh, theta 1 was 0? Oh, all right.
It turns out that if theta 1 is equal to 0, then h of x is just equal to this flat line, right? It just goes horizontally like this. And so measuring the errors, we have that j of 0 is equal to...
Why is this one here? This was like what was it, 0.58 or something, but why is it up here? Well, yeah, why is it up here? Why is it not down here? Oh, was that because of the theta 1 we were using? So, okay. I got it.
1 over 2m times 1 squared plus 2 squared plus 3 squared, which is 1/6 times 14, which is about 2.3. So let's go ahead and plot that as well.
So that would be
the value around 2.3. And of course, we can keep on doing this for other values of theta.
Why is that up here? 2.3. 0, 2.3? Is that what's going on here? Why is it not like over here? Oh, because it's... I don't know. I don't know what's going on.
Theta 1. It turns out that you can have negative values of theta 1 as well. So if theta 1 is negative, then h of x would be equal to, say, minus 0.5 times x, right? If theta 1 is minus 0.5. And so that corresponds to a hypothesis, with a slope of negative 0.5. And you can actually keep on computing these errors. This turns out to be, for 0.5, it turns out to be a really high error. It works out to be something like 5.25 and so on. And for different values of theta 1, you can compute these things, right? And it turns out that you compute a range of values. You get something like that. And by computing a range of values, you can actually slowly trace out what this function, j of theta, looks like. And that's what j of theta is. To recap, for each value of theta 1, right, each value of theta 1 corresponds to a different hypothesis or to a different straight line fit on the left. And for each value of theta 1, we could then derive a different value of j of theta 1. And for example, theta 1 equals 1 corresponded to this straight line fit through the data, whereas theta 1 equals 0.5 at this point, shown in magenta, corresponded to maybe that line, and theta 1 equals 0, which I'm going to show in blue, that corresponds.
But I don't understand why this gets plotted up here. Why is it not 2.3 over here? Is the j the y value? Oh, the cost is the y value. I got you. So that's the output. So we're given x and then we get the y. So which brings us back to here, right? Brings us back to this right here. So the reason why he's plotting it on the y, I gotcha. So whatever this j is, ends up being the y on the chart. So if we use 0.5, then we get a y. If we use 0, we get 2. If we use 1, we get just about 1. I got it.
This horizontal.
This is blowing my mind though. Real talk.
So for each value of theta 1, we wound up with a different value of j of theta 1, and we could then use this to trace out this plot on the right. Now, remember, the optimization objective for our learning algorithm is we want to choose the value of theta 1 that minimizes j of theta 1. Right? This was our objective function for linear regression. Well, looking at this curve, the value that minimizes j of theta 1 is, theta 1 equals to 1. And lo and behold, that is indeed the best possible straight line fit through our data. By setting theta 1 equals 1, and just for this particular training set, we actually end up fitting it perfectly. And that's why minimizing j of theta 1 corresponds to finding a straight line that fits the data well. So, to wrap up, in this video, we looked at some plots to understand the cost function. To do so, we simplified the algorithm so that it had only one parameter theta 1, and we set the parameter theta 0 to rho 0. In the next video, we'll go back to the original problem formulation and look at some visualizations involving both theta 0 and theta 1, that is, without setting theta 0 to 0. And hopefully that will give you an even better sense of what the cost function j is doing.
So what's happening here is like, okay, yeah, so we set theta 0 to 0. So this is like a simplified version. This is like a simplified version of machine learning. We're gonna go even more difficult. Then we got parameter learning and all that stuff. Well, we only got like 10 minutes left, so we'll just hang out for another couple 10 minutes here. That was machine learning AMA. How are you guys? Guys got big plans for the week? How's your guys' Mondays going? I'll turn on the notifications. Get back to chill here for a second. By the way, the link for that is in the description. You can audit it if you want. I like it. It's difficult, right? It's like some people hate math, but I don't mind it. It just takes me a second to figure it out. And then when you're streaming it, everyone's like, "What's this guy doing?" So there are a lot of people that come in the chat. They're like, "Well, have you ever tried streaming machine learning or AI design?" Or like, this is what happens when you stream code. People hop in and they're like, they see these graphs. They see these graphs on the screen and they're like, yeah, I'm out, bye. And they don't even say anything. They just leave. It's really difficult to stream code because people come in and when you're stuck, they're stuck. It's just like you have some idea of what's going on. You know the language, you know the syntax. You've taken this math before, or you don't. And I don't know. I like it. But it's all good. I can't wait to see the comments on this video where everyone's just like, actually, you understood the formula wrong, Josh. This is the easiest version of the formula. Okay, I get it. That cinematic standing desk. All right. Seems you are a gamer as well. Well, what made you say that? How you know? How you know I'm a gamer? Maybe. I'm not offended. I don't get offended. I think it's just funny. People that are really smart in things forget that they weren't once, and that seems to be a common problem in programming. Like people like on Stack Overflow especially they're like, why don't you know this? Well, if you just did this or this, it's like, bruh, chill out. We're not all on your level. Andres, what's up, dude? How's it going, my man? Just hanging out. I'm making a video today, how to find React projects. That's my video. I'm gonna make that right after this stream. I'm gonna work on some other stuff. I was listening to Tim Ferriss's podcast with LeBron James and his like secret trainer. LeBron is he's quite the businessman. He's got his own pizza company. He's got his own supplement company now. I don't know. Hope you guys are staying motivated on Monday. You guys got a case of the Mondays? What is your full-time job? You're looking at it right now. I make videos. I teach code. Mondays are disturbing? Nah, dude. Monday's the best day. Monday's the day when you get to restart the week. You can restart. Oh. That's so loud. I gotta fix that. My ears. It sounds like I'm winning the lottery, right? There's something going on. I need to take these alert boxes out. Alert box, goodbye. Chat box can stay. Does Monday still have a meaning to you? I mean, I have a schedule like everyone else, but I would say weekends have less of a meaning when you're self-employed. You don't get vacation. There's no such thing as paid vacation anymore. But it didn't matter because I never took vacation at my other job. Never took sick days. Always came into work. Didn't matter. But I work every day. There's no days off. There's no days off in what I do. If I take a day off on YouTube, I get thrown out of the algorithm. And that's just how it is. But I don't mind, right? I could queue up videos or whatever. Gregory, what's up, dude? Mondays are my favorite days. Mondays are days when I try to implement new systems. Like today, I'm doing Trello. I'm doing this new Trello system. I got Evernote, so I'm marking all my ideas down throughout the day. I'm trying to get done at 7 o'clock. Oh, invested early into Blaze. What else? Yeah, I'm trying to have like a stopping time at like 7 o'clock every day. Because I find myself at about, I don't know, 3 o'clock-ish, 4:30-ish during the day. I start to get like distracted and kind of bored of what I'm doing and kind of frustrated. But I know I still have all this stuff to do. Whereas now, 7 o'clock, that's it. I'm done. I'm ending it. I'm just going to play some games or hang out, walk my dogs, read a book. Rather than just half-ass everything until I get it done. And then I end up staying up till like 10:30. This is a good stream, though. I mean, it's difficult. It's difficult to teach machine learning to people, anyways, right? It's difficult. It's a difficult topic, and then on top of that, you're trying to stream it and explain it to people. It was good. I enjoyed it. Thanks for hanging out. I appreciate you, dudes. Hopefully, you guys enjoyed the video later today. What's the topic for tomorrow's stream? Tomorrow I'm probably going to start working on one of Team Treehouse's things. I might do, I don't know. We'll see. Might just hang out. It'll probably be working on something. I've been trying to redo, I have like a few different topics for streams, like maybe some subscriber games, maybe like, helping people find jobs like we did before, applying to jobs, showing you guys how I do it. Those seem to get a lot of views, people like that. And then auditing courses. So stuff like that. I might have to, I want to see if I can like audit Lambda's school during the day. That'd be cool. Parker always popping in on the last minute. Yeah, we're about to head out. I'm out. Actually, it's 1:30. I got to stick to the schedule. Otherwise, we'll be here for like 2 hours because that's somehow what happens. Or just a quick stream. 3 hours later, a week later, still standing here talking. That's how I do it. So I appreciate you dudes hanging out. Thanks for engaging. And you like the video about applying jobs? Yeah, those seem to do pretty well. Advice to get better in JavaScript: do more JavaScript. The graphs exploded your brain. They're not that bad, man. They're not that bad. I'm the one with the play button that can like go back and forth to what I need for it to click, and then everyone else watching needs something a little different. maybe you need more time, maybe you were missing a certain piece of information that would have made it click for you, and that it can be a little bit difficult when you're watching, but I think I did all right. If anything, if you were here the whole stream, you could walk away from the stream talking about unsupervised, supervised, the cost function, a whole bunch of stuff. Regression, classification. Even if you can't write the code for it, you still understand it at a deeper level. So that's cool. But I'm out, guys. Hopefully you guys have a great Monday, and I'll catch you guys in the React video. I'm about to go strap this GoPro onto my dog and then go have her run around in the snow for the intro to the video. So I'll see you guys. I'm out. Thanks for hanging.